193.
193. All right, so here's where the important stuff starts to happen. This is where rubber hits the road. All right, so as you probably know by now, you have a chipset that is on your hard drive. And that chipset also has a coordinated other chipset that exists on the motherboard for them to communicate with each other. So you're passing commands. So things like Windows, when Windows 95 finally came out, and Windows NT, basically they started separating us from the machine, from the hardware. Prior to 95 and prior to NT or OS2, we really didn't have we always talked to the hardware. If you wanted to do something, you had to write a driver. You had to deal with something hardware-wise. There was a lot of things you had to do with memory and dealing with the hardware. And the whole promise of Windows is basically, well, we're going to live inside of this multi-universe that we control all the equipment behind the scenes, and all you have to do is easily write your program that says, I need a window. I need a sector from the hard drive. I need a whatever, and it's all going through the API. So, but there's the standards, ATA standards, and the ATA standards are all the commands that are possible, and they make a subset. So in other words, you can have multiple drives to have all kinds of commands that aren't normally used by anybody else, but there's got to be a subset that the motherboard manufacturer, the OS manufacturer, and the hard drive manufacturer agree. All of these 5 things will always do these 5 things. Does that make sense? So there is a subset of commands that when you say, give me a sector, that this command is the same, so that it's generically the same for all drives. But a lot of drives have extended commands and have other things that they can do, which is why you're talking about all these other pieces of hardware, Atola and DeepSpar and PC3000 and all those things that have custom the ability to talk to custom commands. They've reverse engineered. They know when you plug in a Toshiba that this Toshiba can take this command and that no other drive can take that command. So that's what we're looking at. So starting with all the stuff prior to any ATA command committee existing. So we're talking early 90s in this particular situation here. Prior to that, we had what's called PIO mode, programmed input output mode. That's basically how DOS communicates with all of its equipment. Anything that you want to talk to is handled literally by whatever application that you're writing. You have programmed it, and it is talking directly and saying, oh, I need this sector, I need to do this. There's no real multitasking, there's no behind the scenes, and there's not a lot of other things happening, and it's very slow. You can almost see how chunky it is. If you were trying to copy something in DOS, it's going to be extremely slow compared to using some UDMA drivers that can pass stuff across a bus and through memory. So, but it's still valuable to us when something goes wrong. Every drive supports PIO mode. You can still drop back and use old PIO mode to communicate with the drive. So if, let's say you're a manufacturer, you're getting quotes from these Chinese companies, and you're picking a chipset that's a nickel cheaper than somebody else's. And then all of a sudden, there's a memory problem, or, because that's one of the big problems on most of these boards and most of the hard drives is they'll have some sort of memory problem or some other chipset failure or something else that doesn't work right. It'll be fine for a while, and then all of a sudden it just fails. So what you're looking for is all the possibilities of all these commands that you can use to get the data from that drive with the lowest common denominator and the highest speed. So you're trying to find that balance that you can still talk to that drive. And that's why I say you could get 80–85% of these drives without opening them, because that's what you're doing, is you're going to use all these commands to attack the drive till you get an answer, till you get something that makes sense so you can get past it. And then you can add on to that. You can control head assemblies. You can do different types of tests. You can just get certain pieces of data. So PIO mode is slow, real slow, but it is still one of the options that we fall back to. And your systems normally don't do them automatically. The DeepSpar, the Atola, things like that, you can program them to do that. But normally, like for instance, when you start up in Windows, it still does this. You still have this option in any current version of Windows. It may be difficult to get to, but you can go into computer management, and those of us that are old enough to remember when Windows 95 came out, this is one of the things that we added. There is a IDE interface, and in your IDE interface, Windows 95, when it first came out, it wasn't until OSR 2, the second version of Windows 95, that you had 32-bit communication. So 32 bits didn't exist at that time. We were doing PIO mode prior to that. So the very first release of Windows 95 was slow, sitting on legacy hardware doing PIO mode, but most of the equipment had the ability to go to DMA mode. But they didn't turn it on by default when you would install Windows 95, because if that failed, you lost the ability to communicate with the drive. So then Windows 95's whole point was you didn't need to use DOS. Now we're booting. So before that, for those of us who aren't old enough to remember, before that what happened was DOS would boot, then you run Windows 3.1. That's what you would do, sitting on top of DOS. You still had to do all your memory management. Memory management is actually a bug. It was not a real thing. Memory management, so the way that memory management worked, just so everybody understands, because they still basically use this on some of the things that you're doing. It was a bug in a 286 that then they, after Lotus 123 is the one that figured this out, and then after that, then moving forward, they fixed some of the things in the 386 so that you could switch back and forth between modes. But you have what's called real mode and protected mode. And in your computer, in real mode, it means you can only access the first 1 meg of RAM, is the 640K. And so basically you would have a block of 1 meg. You would have 640K, which was for you to use for your programs, which, you know, Bill Gates famously said, this is all we'll never need. And then you have 384K right here that is for system. So this is drive things that the system needed, hardware, equipment, files, whatever. Well, this left a little tiny gap that was just below. I don't remember exactly how far. It's like 16K below the 1024 boundary. So after what they could use, they couldn't use a small chunk of it here at the end. Well, what happened is they wrote a driver called HighMem. So HighMem.sys points to this location, right at the end of that boundary. And when you used HighMem.sys, what would happen is it would overlap and use 64K. So it needed 64K. And so what ended up happening is the remainder of this space now, if you had more memory, and so if you had a 2 meg stick instead of a 1 meg stick, you can now address outside in real mode this particular piece. So you could swap in and out and page your memory in and out. So that's pretty much about where kind of paging kind of started. In this entire process, you're actually taking a chunk that you're using and swapping in and out a chunk of memory over and over and over again every time your system needed it. Oh, I need this chunk, and it will keep swapping it, and then swap it to disk. So that's where that kind of came in as a whole. So we're going to kind of take advantage of all this. What ended up happening in protected mode is that now what happened is if you had 4 gigs of RAM, you could just use all 4 gigs. So this is what Apple always did. Apple started out with the Macintosh, and they had a flat memory model. So this flat memory model allowed them to use whatever memory that they were slapping into the machine in the first place. So when they wrote it, that was a pretty good idea, so that they didn't have to sit here and deal with memory management like we had to deal with in a PC. But ours is all about legacy. So as we're gradually moving forward, we have to get out of real mode. So Windows 95, Windows 98, Windows 99, Millennium Edition, or whatever the crap that is, those editions, anything that said DOS, Windows 3, and then up through Windows 99 Millennium Edition, those are all real mode operating systems. And they always have to swap in and out in order to get into protected mode and switch back and forth. Starting all the way back prior to with the Mac, and then in the PC world, we had OS 2. Anybody remember OS 2? You still use it every day. You just don't know you're using it. No, Windows is OS 2. IBM and Microsoft had a little bitch fight, and they broke up. And they had a code sharing base, and IBM was making OS 2, and Microsoft was over here making Windows 3.1. Microsoft wrote the programmer's interface for and the whole Presentation Manager. That's where Presentation Manager came from. Presentation Manager was for OS2 and its multi-use kernel, and it used a particular file system called HPFS, High Performance File System. And all this stuff was written all the way back in 1983. It was supposed to, IBM never intended for Microsoft to be the company it was really going to hire to write its operating system. They gave them DOS, and it was going to be like their throwaway. Here, somebody can make something over here for our first machine while we work on the real shit. Right? That's what was happening. So they were working on a multitasking, multi-threaded operating system, and Microsoft did work with them. They did hire them and have them work with them and do the whole thing, and they did have a code sharing base, but IBM intended on going a different route, and they didn't like Presentation Manager. They wanted to hire another company, the company who made Geo's Ensemble back in the 80s. It was already a Windows platform. It was running on the Apple. They were going to hire them to do all of their development and everything going forward. And Microsoft found out about it, and Microsoft's Windows platform, I mean, they definitely are the better marketer. Their Windows platform, once they started creating the Windows platform and taking over, starting writing apps. I mean, all you really need is a killer app. Once you have a killer app, then you win, basically. And Windows 3.1 was still pretty kludgy. I mean, it was, you know, but that was the first way that Lotus 123 could run on a system and use protected mode memory, so you could have a big spreadsheet. That's the winner. That's how they won. And then the quote was, "Excel's not done till Lotus won't run." I mean, I don't know if you guys remember all this stuff. There was a big battle of Microsoft trying basically to use the operating system to kill other products, and that's basically how they got Excel to become kind of the big forerunner of all the stuff. Anyway, so we're talking early 90s at that point. But they still didn't have a real mode operating system, and they still didn't have any other way. Like, you still had to boot DOS, and then you had to run this executable to get Windows to run, and then it would switch into protected mode, but it couldn't switch back to real mode on the 286. So that's 90 or so, and then we're talking 92, 93, we got a 386. And now we're switching back and forth in modes. The 386 fixed it. It can switch from protected to real mode back. You don't have to reboot your computer. Then, before that, you had to reboot to make all your stuff work. So anyway, the whole point ends up being this, is that going forward from there, when Microsoft and IBM had the little bitch fight, Microsoft had the code shared base for 5 years, and IBM started embedding Windows into OS2. Well, eventually, IBM, being the terrible marketer and the terrible thing that they are, messed up. And Windows, basically after 1993 or 1984, Windows 95 was the killer. Windows 95 killed OS2. OS2 was a far better operating system. Multitasking, multi-threaded, all the other stuff. But because they had a code sharing base, then that's where Windows NT 351. You guys remember Windows NT 351? Basically they sent out a mailer saying, we're not going to support OS2 anymore. We wrote the programming operating languages for you to compile to be able to do, you know, I don't know if you guys remember, like Microsoft C, Microsoft Pascal, Microsoft Turbo, whatever. Anyway, so the whole point ends up being this, is that now Microsoft takes off. They release Windows NT 351. It was not a real big winner, but it was the first protected mode flat memory model for the for operating systems, and that later became Windows NT, then Windows 2000, and that's the base OS. All the others have new generations of code from there on, from XP, 2003, 2008, and so on and so on. But that's where the base came from, was from OS2. And what's our file system in Windows?
NTFS.
NTFS. What does NTFS stand for?
This idea. New Technology File System.
New Technology File System. You know what its name was before it was New Technology File System? Nope.
Old system.
Nope. High Performance File System. It was OS2's file system. As a matter of fact, there's only one byte that's different in the whole file system. So everything that was in OS2 for HPFS all the way back to 1983 is the same thing that's in NT to this day in version 5. It actually still will say in certain places that I am HPFS. And you'll see it in certain locations. The identifier, the string, the whole thing, all Microsoft did was change the 17th byte and change the string from HPFS to NTFS. So all the strings that are in the file system say, but they were the same. It's the same file system we've had since 1983. So it is not new in any way, shape, or form. It's been around for decades. I mean, it's a genius file system. And I've talked to some of the OS2 developers. I've talked to some of the guys who wrote some of the books and some of the stuff. It's a genius file system. And I'll go through some of that as we're going through it. But this whole model and how this actually came to be is really important from a standpoint of why we're at the spot that we're at. It's still a legacy thing. But the one thing that I was trying to show is Windows 95 was the first one that we finally had that could start doing 32-bit. And inside of Windows 95, there was this properties window, and in the properties window there was this box right here, advanced settings, and you could switch. Before this was available in OSR2 was Windows 95. It was only 2 system developers, system builders got OSR2. You couldn't get OSR2 off the shelf. They started selling it like a year later, but when it was first released, OSR2 was the FAT32 file system. FAT32 wasn't in the first release of Windows 95 either. It was still the base of FAT16. FAT32 came in OSR2, and then they added this ability to do DMA. Now it replaced everything right away. Like none of the original releases of Windows 95 survived. Everybody immediately upgraded and then switched to DMA. And then your hard drive was able to communicate over direct memory access, so it did not require every action to be taken by the CPU. Before that, it was super slow. So, and the main reason to do this, there was one main reason, and one reason that Microsoft won all of these things, and that has to do with games. The entire point of Windows 95 was it had DirectX. There was a party. There was literally a party on the night that Windows 95 was released. CompuServe hosted a party all over the world, everywhere they had a store, and it was a midnight party. It was maybe the first release party that I think I've ever seen. I went to. And so you show up at CompuServe at 10 o'clock when they closed, or CompUSA when they closed at 10 o'clock. They opened it up just for all the geeks that were showing up for this event. And then they had hired John Carmack from Doom, the guy who made Doom and Quake and all these others. So they hired him to remake Doom for Windows 95 to run in a window. So he, instead of using OpenGL, because he was a big OpenGL fan, he wrote drivers, he wrote everything he needed to write in DirectX. And they paid him, they must have paid him a boatload of money. I don't know what they paid him, but he wrote Doom so that it could work through DirectX. And DirectX is a hole in your operating system to your hardware. So basically the whole point is I could write a driver, and when I run a game, it suspends everything else so that multitasking operating systems don't get in the way of your system, because we had really weak processors compared to today, and it basically made a hole to the hardware. So your software and your driver could talk to your hardware without you having to do anything special. And the reason I say that, what was important is before that day, if you wrote a game, you also had to write your video driver. Before that day, if you wanted to play chess on a computer, you had to write your own video driver. So that's why people started using, I don't know if you guys remember those 3D Monster cards. 3D Monster, it was the competitor to NVIDIA, and they didn't survive. I think they actually got bought by NVIDIA later on. But they were the competitor to NVIDIA, and the whole point was they had a set of drivers that if you were a developer, if you had this game card, then it would switch to this game card, and you didn't have to write your own driver. So a lot of them started requiring you use this Monster 3D card driver, or whatever it was, so that they didn't have to write their own driver because they weren't good at writing that. So this appears in Windows 95 and later, and from then on we're in DMA mode. So from 95 on, we now have DMA. We can switch back and forth at any time we want. You just can't do it on the primary controller. I'm on the primary controller. Remember I told you if you have a second SATA controller or something in your computer, you can do a lot of other things that you can actually do for recovery. You can actually go to your secondary controller and you can put your secondary controller in PIO mode manually and then try to copy your hard drive, and it might actually work. So the things that, so I'll tell you, DMA is a huge problem. In data recovery, one of the first things that ends up happening in most of the systems is it does one pass with DMA, and then whatever it fails on, it goes back and picks everything up with PIO. And there are times that it will not work in DMA mode at all. You plug in a drive, you try to read it forward, DMA doesn't ever work. You run PIO mode, it picks up everything, but it's slow. It's about 16 times slower than you'll get in DMA. So a 1 terabyte hard drive will take you 16 times longer. It could be a long time. Get my point? But this is the whole point, is these things exist. So this is the poor man. Now if you're in Linux, you use HDParm. You can use HDParm to set your parameter, and you can switch to PIO mode. So you just can't do it on your primary controller because you're booted on it. Okay? Everybody good? Long explanation. So then ATA command. ATA starts to exist as a body. So it literally requires a body of businesses to get together and decide, here's all our commands, and this is what we're going to use. So all the vendors, Microsoft, Intel, everybody who was a leader at the time basically got together and created what's called the T13 group, which is now also the SATA group. So the SATA command group, those were all the bodies that came up with the programs, the certification, the process, because they were the manufacturers of all this equipment. And so that was where that started. So then you get PIO mode 1, 2, and 3. Those are, it got faster through all the different modes. Then you got direct memory access, and then they finally added the ability, because we now have IDE drives, to add master and slave, so that you could use 2 different brands of hard drive together. And you could tell one, I'm the master and I'm the slave, so you could have 2 drives on the same chain together. Right? So on SATA drives, do SATA drives have a master and slave jumper? No? Why is that?
Because everything gets controlled by our drive itself. You don't have to tell them what it's doing.
Right, but you know why? I'm going to tell you why.
Most people are idiots.
That's right. People are idiots.
That's what you said on your video.
That's right. People are idiots. There was a meeting of the T13 group. They get together and they say, what's our most expensive thing? It's the support call to ask where the jumper is. That's the only time we ever called. I mean, I remember calling manufacturers to talk to them about their compatibility with other drives. And then they eventually came out with the cable select, which was, okay, we have a twist in the wire, and if you put it in the first place, then if it's cable select, it'll be in position 1, and then it'll be in position 2 automatically. You didn't have to do anything. Of course, that didn't work great either. That still had problems. So sometimes 2 manufacturers didn't work well together. So, so they actually said, I swear there's a document, there's a transcript somewhere for this meeting, and they said that you are too stupid to have a jumper. That's what they said. So that was immediately the thing that said, well, we're going to get rid of this whole support cost, because they had to have people answering the phones just because you couldn't figure out where the jumper goes. So they removed the jumper. They're now hard-coded. They're actually hard-coded for master or slave. You can still put master and slave on the same chain. You just have to be an OEM or a manufacturer and make it that way. You can't buy them that way. You have to know what you're buying. So that's why there's no jumper anymore. That jumper is now used for speed and for technology stuff. So updates, firmware. You know there are firmware updates for your hard drive? All your manufacturers have firmware updates for your hard drives. You can actually go and download a firmware update and patch your hard drive. Nobody does it. Nobody does it. Only the automatic stuff like IBM. The Lenovo's have an automatic driver that goes and looks for their updates and puts them onto the drive. They actually have hard drive updates. But nobody else seems to do it. Maybe Dell does, but Dell's got a couple.
For the Seagate.
Yeah, so the Seagate patch, because they had a huge bug, there was a firmware update. But there were other firmware updates. It's just that nobody installed them automatically because none of your systems have an automatic search for your hard drives update and put it on. It's not part of the Microsoft distribution.
Although you do it, it's a fresh reinstall and go directly to the website and download all the
right.
updates. That's the only
Yeah, and you're right, because you don't know what it'll do to your data, right? Yeah. It feels freaky, like, but IBM's do it every day. IBM's have it in their standard update process, and hopefully somebody tested that and make sure it doesn't actually wipe your hard drive in the process. But that is a problem in SSDs, right? As you know, if you update SSDs with some of their patches, it wipes the drive. It's got to be fresh in some of those.
I do it when it's a fresh, installed, clean driver.
Right.
That's the only option. I never do it afterwards.
And you're right to be that cautious, I think. Okay, so from there, ATA2, and I'm only mentioning the stuff that matters to us. I'm not mentioning, there's hundreds of things in every ATA spec. In ATA2, this is the first time we went to LBA blocks. Prior to ATA2, we did not use LBA. Logical block addressing has been around since SCSI. And SCSI's always had it. Old SCSI hard drives, even like a 1 meg SCSI hard drive, will still work on current equipment because they used LBA blocks. It'll still run if you can get the right connector. It'll still work. But we didn't use that in IDE hard drives. We used CHS, cylinders, heads, and sectors. And we had to manually enter in all these parameters in order for it to work so that we could tell it. What's that?
Legacy.
Legacy stuff. There's actually been between 4 and 5 different ways that we used CHS. And every time that we hit a boundary, we had to come up with a new way. So 4 gigs was a boundary. And there was a time period where in the 90s that 4 gigs actually locked us in on NT to a 4 gig boot partition. A lot of people didn't like that, so they ended up going to a second version, which was a 8 gig partition. So there actually was a second version that allowed you to do 8 gigs. And then after that, they finally gave up. They finally said, fine, let's go to LBA. So now we're going to use the same thing that SCSI's using. So we're talking 85, 6, somewhere in there. We finally got rid of all the other stuff and we use LBA. And that allows us to use any drive up to the size that LBA can count to. Now, when I say that, what I mean is this one, the very first release of LBA, was 28 bits. It originally is 32 bits. It seems like a weird number that you're going to have 28 bits. It actually is 32 bits, but they took 4 bits for reserved flags. So they're using 4 bits from that, and so they allocated 28 bits to us to count how big our hard drive was. So that's what's happening, is it's a counter that says, how big can I talk to a hard drive? Now imagine you're making this decision in 1994, 1995, a year or two before it's released. You're making this decision and you're saying, fine, this is all we're going to need to use. What was the size of our hard drives, say 1993, 1994? What do you think?
40.
Nope, way less than that. 10 times less than that. We were somewhere in the 2 to 3 gigs range at best. At best. We were just barely hitting the 4 gig by 1995. And then 8 gig by 96, 97, something in that range. Remember, 10 gigs was the largest drive we had at the beginning of 1999, was 10 gigs. So in that whole range, we were way below that. So if you come up with a spec and you say, hey, no matter how fast we've been working through all of these things for 2 decades, 28 bits allows us to go to 137 gigs. That's the number. The end number of 28 bits, if you count in 28 bits, is 137 gigs. That's an important number. You'll see it sometimes. It'll show up in drives. When you take a drive and you put it on an old system, it'll actually partition it as 137 because that's a 28-bit system versus a 48-bit system. So there is a difference in these. Now, the important part in 28 bits is, first thing is we had small hard drives. They thought it'd be decades before they would hit the limit. Of course, we know now, in the turn of the century, we ended up at 20 gig drives, and then as soon as we got from 20 gig drives, by 2001, 2002, you remember we already were at 200 gigs? By like 2002, we were at 200, 2002, 2003, we were in the 200 gig range. You could buy them, they were expensive. But at that point in time, you had to upgrade your BIOS. Your BIOS could no longer talk to the hard drive if it was larger than 137 gigs. When we made the ATA command set for number 2, we also had one special command. Super important. It's called, and I don't actually have it documented in this piece. You'll see it in the process. It's so it's called a long read. A long read means, I don't mean there's a new command called long physical read. That's a big sector. That's a 4K sector. The old command was just called long read, or it's also known as ignore ECC. Now that's a very important command. Ignore ECC means this. I've got 512 bytes, and at the end of 512 bytes, I got 4 bytes of ECC, error correcting code. What if the 4 bytes of ECC is what's wrong? If you read 512 and you had 4 bytes of ECC and it was incorrect, what happens is it returns 0. You don't get a sector. When I ask to read a sector, it's gone. You get 0. That's why your forensics tools all put zeros there. They don't know how to ask for the data. Is everybody with me? That's a very important command. We can actually manually implement that command in ATA command set 2. We've got to be in ATA 2, and we have to ask for ignore ECC, and it's a guess. Remember, if you don't compare it to a ECC, what you get is 512 bytes of a guess. Okay? So the way that the DeepSpar is the best at doing this. Out of all the systems, DeepSpar is best at doing this because they build an array. DeepSpar will soon have that function. It does not currently, the Atola does not currently have the function to build an array. And what I mean by this is, if you're reading a sector and you have a ignore ECC, it's a guess. You read it once. Normally the drive only reads and returns once. And you can say, give it to me anyway, even though I know you're going to say error, give it to me anyway. So you get 512 bytes. So you read it again. You make another one in an array. You can read up to 99 of those. You can read it 99 times. And then you can look at the bits one at a time in your array, and you say which one won the most. Which one was repetitive more than anything else. And it will select those automatically. So the DeepSpar does this automatically in ignore ECC mode. So when you're looking at a DeepSpar in front of you, there's an option. I'm just going to show you real quick where these items are. So I'm going to go through all the menus. You don't have to remember where everything is quite yet. So there's a settings menu, a configuration menu, and then there's imaging process. These 3 are the ones that control the device, the whole device from that standpoint. And it kind of works backwards. Settings are hardware, timing, and ATA commands. Image process is basically a list of which processes that you have hard-coded. You get to label, I want this pass to do this. I want this pass to do that. And it's a list of them. So real quick, settings is hardware. So this is all the timing. There's very few tools that will do this too. Very few. The PC3000, the Atola has some of this, but generally speaking, most of the older hard drives, some older hard drives don't work on the Atola correctly because it doesn't have some of the timing functions. So this is all based on hardware. What happens when I turn the power off? How long does the power stay off? When I repower the drive, how long does it take for it to pulse and come back up? And you can play with these settings if you have a really old hard drive that won't work normally. And you know, usually because it never seems to refresh in the screen, things will sound okay on the hard drive. You won't hear anything that sounds weird or anything. You can actually play with timing and increase that. I don't have to do it often now. I used to have to do it more often than today. So keep these things in mind. I'm not going to spend a lot of time on these right now. These are things you play with when things don't work right. But right here, force LBA 28-bit mode instead of 48-bit mode. So as we got newer hard drives and we went past ATA2, we got 200 gig drives. It can no longer work in LBA 28-bit mode. So they upgraded it to it's really 64 bits, and then they took 16 bits of reserve space. So that's why you ended up with LBA 48-bit. Okay? So that's what ended up happening, is it stole some of those for reserve flags, and then 48 bits is now our current usable standard. When they went to LBA 48-bit mode, they said, you know what? There's this command called ignore ECC that we don't need anymore. This is obsolete. So they obsoleted the command. So in LBA 48-bit mode, you cannot read technically correctly ignore ECC. Now I'll explain, there is a way to do it, but it's not very efficient. It does work, just not great. In LBA 28-bit mode, it works fantastic if your drive supports it. Some drives don't support it, like Samsung's don't support it. Toshiba's don't support it. And those are mainly because they didn't have anything back then. They didn't write the code, they didn't have them. So they just kind of skipped all that altogether. It was already obsolete past the time that they were using it. But Western Digital and Seagate were around, and most of those drives will still support that ability to do that in the older settings. So this is where you choose which mode you're going to be in. You have to physically check a box. You can still do it while the system's running. You just can't do it on the fly. You literally have to come into settings and check a box. Everybody good? All right, so we'll talk about these other things later. Not important, not important, not important. I just want to make sure everybody knows we have the ability to change hardware ATA commands, and that's what that means. And I'm only going to do this because I'm going to do something called the long read. And when I do a long read, I'm going to get a better chance of reading data that's damaged, that no other device can read. Everybody with me? What's the largest size that I can read?
137.
137. That's the largest size I can read. After I pass 137, then I've got to switch, or it will switch for me to LBA 48-bit mode. Okay? So,
Beyond the 137.
what's that?
Beyond the 137.
Yes. Right. But beyond 137, but now keep in mind, even though it sounds limiting, where's the most important part of your data? It's almost always in the first 100 gigs, right? Your first 100 gigs is your OS, your tables, your MFT, your NTFS setting, all that stuff. So luckily, it's in the beginning of the drive. It's rarely someplace else. Now, it can be. It's possible, because where can we make a partition? Where?
Above that?
Yeah, we can make a partition anywhere we want, right? So if you make that your boot partition and all your data is there, well, something might be in the first 137 gigs, but it might not be the table that you want. Does that make sense? So that's the only downside from that perspective is those particular items. So, all right, so back to this. So that's where we're at in ATA 2. Then ATA 3, this is horrible after we got some sort of power outage problem.
You sometimes play around, Scott, with that settings.
Yes.
I tried.
Yes. Yes, but not every drive supports it. So you're really testing first to see if the drive supports it. If the drive does support it, it's the most useful command on the deep SPAR period. In my opinion, of all the things that separates men from boys, that is the thing that makes the difference. Because if so let's say Frank's got a case going on and he doesn't have a deep SPAR, and he goes and he images a drive using in-case, and the in-case comes back and says, I got 137, or let's just make another number so that nobody gets confused, 10,000 bad sectors I couldn't copy. I have a list and it says there's 0. You're testifying in court, right? And you're going to bring up your list and you're going to say, yes, it's okay though, I know there's 0, but this is normal, this is what happens when I got bad sectors, so it's best case scenario, right? He's done, he moves off. The prosecution, the defense or somebody probably said, do you know what's in those sectors? And he goes, no, there's 0. I don't know what's in them, there's 0. Scott gets on the stand. Scott ran Ignore ECC. I read all of them. I made the best possible guess possible. I set that to 99. I built an array. Every time it got 512 bytes, maybe 1 or 2 bytes was wrong. And so I get, maybe I get 510 bytes out of that entire sector that looks perfect. And I can actually reassemble a JPEG. Because I could technically do that. One little chunk could actually make enough for me to actually be able to do that. I'm on the stand and I'm testifying. And I'm sitting in front of the jury. It's a jury, right? And then I say, all those zeros he got? I read them. I got them all. I'll show you exactly what's in there. Some of these are a little bit of a guess, but look, you can see what it says, I am not guilty. That's what it says in that spot. See the power? That's the power. In my opinion, that's one of the things. But the other thing is too, is that also means all those places where you had a database or you had something else, you might get just enough data and it might be just perfect enough. It's not always perfect, but it's pretty good. It's a pretty good guess. It's better than any other system that there is out there at it because it's the only one that builds an array. And they've been doing that since, you know, they changed it. It was a byte array and it's a bit array now. I had some problems with it and I couldn't get some of the guesses right or something, and they ended up switching it in the next version to a bit array. And so from like 2007 or 2008, it's been an array. It's been a great bit array from that standpoint. So that's one of the best things you can use. So keep this in mind. It's very important, and it's a big portion of exactly what you're using a DeepSpar for. Other tools do it. The Atola does have that setting in there. They just don't build an array. He only reads it once. The PC3000 only reads it once, which I think is a big failure. I've told them 100 times and they don't get it. They don't understand why I want more. They don't get it. So I've made them videos. They don't listen. So SMART, self-monitoring analysis and reporting technology, IBM added that into their drives in the ATA3 spec. There's a couple other things that were added into ATA3, but SMART is a big one. Most of the time, in the early days, SMART was disabled because if a manufacturer made a drive that told you that it was going bad before the warranty was over, it cost the manufacturer money. So they turned it off. So even though it was able to predict it, it wasn't used because the manufacturer was afraid that they were going to have to spend money. Also, there's a liability issue. If the drive tells you that I know that I'm going to go bad and then you lose all your data, then you feel like that the manufacturer is responsible, that they knew that these things were bad. Does that make sense? All right. So ATA4 adds HPAs. Now, HPAs are called host protected area. Anybody use host protected areas? So in data recovery, I use it every single day. Every day I use an HPA. There's another version of this which is called a DCO, and basically it's the exact same thing. It's right here. It's a device configuration overlay. The issue is that HPAs were done by Gateway. Gateway asked for a command so that they can separate off a piece of your drive. They can put all your CDs and DVDs that they were going to mail to you, that they cost them money to make, and they wanted to put it on your hard drive, and it's a real benefit to you somehow that you have to create your own disk before your disk dies so that you can actually restore your own system with your own DVDs that they decided not to mail you. Get my point? And they stole drive space from you. It's like the biggest thing that has ever happened, that they've stolen everything. They took your drive space, they put your DVDs and CDs on there, they didn't mail you those, and you have to buy your own CDs and DVDs and recreate your own images, and then it still doesn't give you your disk space back. It still keeps your disk space. So it reserves space. It's called a host protected area. I'll get into what this is in a minute more, but this was what happened. That's Gateway. Then when we got to ATA6, the device configuration overlay was Dell and HP, and those guys wanted a utility partition. They wanted a partition they could boot into that they could run their utilities from that says, I'm going to test my machine, or I'm going to tell you if something's bad, or warranty, or whatever. And so you can actually use both of these together, but it's basically stealing space from your drive. That's really what's happening. They're just chopping it off. I don't use DCOs. They'll exist on drives, but I'll just ignore them. But I use HPAs. Again, I'll tell you why. Now, the other one that's important is ATA5. CF cards, compact flash cards that professional photographers use, are the only memory, the only one that has its own ATA spec. Why is that important? Because I can actually treat it like a hard drive. If you give me a compact flash, I can boot on it just like I boot on a hard drive. I format it the same way I format a hard drive. If you gave me one to recover, I can plug it straight into the DeepSpar as a hard drive. It is not memory, even though it looks like memory. And it wasn't originally memory, it was originally a spinning disk. But they made a little micro drives. But now they're all compact flash, they're all memory. So that has its own spec. So if you have to do a data recovery on a compact flash, treat it as a hard drive, do not treat it as memory. Understand my point? That's a huge difference in memory. No other memory does this. No SD cards, no micro cards, no Sony card, none of them. None of them have their own spec. They are all memory, and they all convert to USB before they convert to something else. So if you wanted to connect one to a hard drive and you wanted to put it on a connector so that you could boot on it, It's still USB. It still connects to USB before it connects to anything else. No matter what adapters you buy, there is no raw adapter that gives you access to it as a hard drive.
So which one do you use? ATA5?
Yeah, ATA5 is, it'll just treat it as a hard drive. Once you plug it in, it's the only spec. So CF will identify itself under ATA5. So any drive, anything you connect it to, it will automatically tell it, I'm ATA5.
How are you plugging it in?
There's this little Zif socket. All connectors. So no matter what you're looking at, so you're used to seeing this and this, right? Everything else is just a version of these. All of them are versions of this. They're just adapters. So you have an adapter and you plug the adapter in and then you plug your device in. So almost everything else is a PATA adapter. Zif sockets, converters, all the other stuff is just an IDE to PATA adapter, parallel ATA adapter.
So there's a specific adapter for the CF card then?
Correct. There is a specific adapter for CF cards that plugs straight into the PATA cable.
And another one for flash sticks as well?
Another one for what?
You can do flash sticks as well, like normal memory sticks with that or
No.
not?
So
Only that.
you can buy adapters, but they are actually USB devices in between. So it converts it to pretend I am an adapter, and that's what I'm trying to say is there's a chipset in between that controls it, that when you plug that in through an SD card or any other kind of memory, they're not real ATA specs. They're converting it to USB and then pretending. So you don't have raw access to it. It's always converted and running through a chipset that controls USB.
So in other words, if you had the adapter, it wouldn't be the same as plugging it directly into a converter that goes right to the CF card. In other words, a USB adapter. If you plug the CF card into a USB adapter and plug that in, that would...
Yeah, that's not the way. Right, exactly. It negates it.
Right.
That completely ruins the whole idea. You can actually take CF, even though they come in those little memory blocks and those other things, you can actually take, there's a special Zif socket version that you can plug straight into the PATA, and it plugs straight into that. It's just a converter. It is PATA. So it is a PATA adapter. Understand what I mean? So just don't use the ones that are USB.
Where did you buy that adapter?
I mean, they came originally with some of the devices, but I'll find one on eBay or whatever. And all you're looking for is CF to IDE. That's what you're looking for. It's called CF to IDE. It literally, you'll find one online somewhere. But it just looks like an ordinary, and all of them, the same ones for Zif sockets. You guys have seen the Zif socket ones, right?
So can I see that adapter?
Here, I'll bring it up.
Is that like the old zip drive?
So Zifs are zero insertion port sockets, and then they look like, it's not these. These? You've seen these before, right? They have this little thin cable right here, and then you plug this in and it plugs in. So there's all these different, right here. These are all the Zif Socket Boards. They go for the 1.8-inch drives. You've seen these before, right? No? So if you pull a 1.8-inch drive, they're a little square drive about that big. Those are Zif sockets. They have a special little cable on the side, and all they are is they snap into this connector right here. So they have two different kinds. There's two different kinds that exist, and they have these little flat ribbon cables that are easy to break and bend. So you usually buy like 10 of them because you're going to break them. And then you plug them into this Zif socket, and this thing just snaps down. Well, all that is converting it. This is converting it to SATA. But they are PATA. All those drives are actually a PATA drive, so that's just an interface change for that. That's all it's doing, is converting that from one type to the other. This is what the ones will look like for, so this one says 1.8, but that's exactly what it looks like for the CF sockets too. There is a CF socket that looks exactly like this. So the pins, it's just pinouts that are just changed coming through to the device. So, but all of them, everything is one of these things. So This is called CF to IDE, and you're just trying to find one that doesn't have all the electronics in between. So this is just a compact flash adapter. See, this comes out. Look, there's not really hardly anything in between it. What's happening is you plug in your compact flash, and then it comes back out as an IDE adapter. And they make simpler ones than this, but that's what you're looking for. Is you're looking for any of these that are compact flash to IDE adapters. So, and these have jumpers for some different versions or something like that. But see, you can even see master, slave, like everything. It's exactly the same as a regular drive. It's see? That is not converting to IDE. That's going out the normal way. But when you buy like one of those memory, when you buy those ones that look like this, I don't know, there'll be a whole bunch that will have, and that, you know, you have your multi-adapter, and one of them will be CF on some of the ones that you'll have. You'll have multi-adapter plugins. You can't see that very well, but you get the point, right? All of those, even the ones that go to IDE, are not for IDE. They still have, dang it, like all of those other interfaces that you're putting that in, that's still a converter. This still converts it to IDE, I mean to USB on its way out before it does the connection. Okay? So that's what I'm trying to say. The only one that's really important is CF. When you're doing CF, you can actually treat it as a hard drive. That's why it's bootable. You can format it the same way. If you get a big CF card, you can actually install Windows on it if you want. As a matter of fact, I think that's actually how the Atola runs. I think the Atola has a CF card with an OS on it, and it's booting on it internally, and then it has a second one for logging. So I believe they're actually possibly removable even. Anyway, so we already talked about that. We talked about 48 bits, and then 48 bits disables some commands. Now, what happens in 48 bits, if I use ignore ECC and it works at all, if I can use ignore ECC in 48 bits, what happens is the drive dumps it to memory. Then the deep SPAR reads it from memory. Understand what I'm saying? So it's reading it from the memory on the drive, not directly a dump from the drive itself. When you read a dump from a drive and you get it directly from the source, there's no other crap in between. But in memory, if anybody's ever done memory analysis and stuff, you'll know that sometimes when multiple writes occur with memory, that there's junk sitting in memory, and whatever junk it doesn't overwrite is the same junk that was there before. So when you're copying that junk out, it's less accurate. Everybody understand what I'm saying? It's still better than nothing, but it's less accurate. It's not as accurate. So more tries are needed if it's in LBA 48-bit mode than 28-bit mode. Everybody good? All right, so now, this is the summary of these items. We have PIO mode, DMA mode. Now there's about 8 different types of DMA. There's DMA, there's 3 different types of DMA, and then 6 different types of UDMA. And you're looking for the sweet spot. So I'm going to talk about these again. You're going to see these in the deep SPAR in a few minutes. So you'll see it used practically. I'm teaching it to you for a reason. Then you have LBA 28-bit and 48-bit mode. Those are all your transfer ways that you can read and write that affect the drive from a hardware perspective. Those are the ones that we're talking about. PIO, DMA, UDMAs, all the others, LBA 28-bit and 48-bit, so that we can switch read modes and different ATA command sets. Good? Everybody happy so far? All right. Now, let me talk about host protected area before I jump into that real quick. Here is, it is way simpler than people make it. People get really confused all the time by HPAs. It is very simple. Let me explain what happens. Here's your hard drive. On your hard drive, you have a system area. Everybody knows this now, right? So that is your system area. Inside the system area, remember I told you, you have geometry. Your geometry is written there. You know what your geometry is, right? All it says is, how many LBA blocks do I have? So if my drive is, 195, gigs or whatever, then it's, 200 and something LBA blocks. And that number is written there. Well, after Gateway asked for a way to chop that, they added a second table. So there's a second one right here. And this table says, well, this is my native now. So this one now became version 1. This one now became native. That's my actual true maximum size. But all the operating systems and your motherboard agree that if you boot on a drive that there is something in this box, we will accept that box as the real size. I'll ask you if you tell me what this size is, but I'll always accept and chop it off here. So if let's say this is 1 million, 1, 2, 3, okay? I've got 1 million sectors in my native. But I tell you, well, I only want 500,000. And I write that there. Every time I boot, my disk is half its size. Understand? The native size, if I ask the hard drive what its serial number and model number and all of its geometry is, it'll tell me it's this. But for all intents and purposes, once it's booted, it's now going to always be half.
I'm sorry, who puts that there?
When somebody decides what their size of the drive is going to be and writes it there. It could be manufacturer, it could be Gateway, it could be you. You get to choose, okay? So for a while this wasn't available to us as a command that we could actually change or implement. But now we can. We have tools to get to this, and we have tools to do everything we want to the drive. So we can actually write to the system area AHPA. Now, what this does is, all it says is my drive is smaller than it was.
Okay, and that's the host protected area, that's what you're talking about?
Correct. Host protected area. So if this is my drive, and I have 1 gig all the way from here to here, and now I've said I'm going to have 500, then it's literally cutting it off right here. And so now I'm just going to have a smaller ring, and only this outside edge is available. It's always cutting it off of the tail. Understand what I mean? So what I'm saying is, I'm going to say it again. So if whatever number I put here is from the beginning of the drive that far. So it cuts the end of the tail off as it's unusable. It shoves that away.
Is that what it's called? Unallocated data?
No, unallocated data is when your operating system has already deleted something that's long gone and it no longer tracks it. When you first delete a file, you have an MFT. You have a table that keeps track of, I deleted a file. Now when I say deleted, I don't mean trash can. Okay? The trash can isn't deleted. The trash can is reallocated to another location with a pointer, but it doesn't actually do anything. It just renames the file. When it's unallocated, that means that now the operating system has decided I no longer need this data at all. And so now it's removed it from its table for some reason, and that stuff now no longer exists in anything that's trackable. No metadata. So it's really about metadata. There's no metadata that goes with that data, and that would be unallocated. Okay, so back to the HPA. All it's doing is chopping off the end. So imagine this. I give you a 200 gig drive, but I tell you my original source drive that I'm copying the data from is 40 gigs. So I want you to make the 200 gig drive a 40 gig drive. Does this make sense? So there's a command inside of a deep spar to do this. So here's the thing. So my original drives, come on. Well, I have killed it. It's pretty rare, but it happens. So from the beginning, if you had to reboot your DeepSpar today while you're working on hard drives, if you have to reboot this DeepSpar, it initially boots into DOS. So it's using Caldera DOS, which used to be Dr. DOS, which was Novell's version. That was before that was DR DOS. So which was Deck Research or whatever. So